Hi everyone, so today we're going to see how to fine-tune an LLM on your own data. Super simple. Now, for this tutorial, I built my own data set. I wanted to fine-tune an LLM to write in the style of Paul Graham. For those of you who don't know, this is Paul Graham's website. I really like his writing style. He's got lots of essays here. He's got like a very simple and clean style. So I scraped these websites, got all these essays, and then asked ChatGPT for each one of them, automatically of course, to write a prompt that would have generated this essay. So for each essay I have a prompt that was generated afterwards, like write an essay exploring the different types, blah blah blah. So with this data set in hand, I put it on Hugging Face. And then we can get started fine-tuning. We're going to be using LoRA, low rank adaptation. If you don't know what is LoRA, you can check out this tutorial on YouTube explained by one of the guys who invented LoRA. Super easy to understand. And yeah, let's get into it. So of course you have all the pip install stuff, not super interesting. You need a Hugging Face token that should have write access. You get a model that you're gonna fine tune. For this tutorial, I choose Google's Gemma, and you take your data set. So for me, it was Paul Graham's essays, and you write the chat template. So in this case, you got to determine the beginning of sentence token. There is no system rule in this case, things like that. So you run this function on your sample data so that you get this sort of template with role user, content prompt. In our case, this is the prompt, and role assistant, content response, in this case, the essay. Once you run that, over your data set, you can then train into test and split, train and test split, and in the end you have a data set ticked with train and test. Each one is a data set containing either 205 rows or 23, and it only contains text, which is the text generated by this template. Now, next you're going to need this auto model for causal LM, where you get a you use the from pre-trained method, and then you get the model name, you define attention implementation and device mapping. And now for the form part, LoRA config, you can use the library called PEFT, P-E-F-T. You need to define three things. First of them is the rank dimension, so the rank of the LoRA matrices. The smaller this rank, the higher the compression. The alpha is the scaling factor for the LoRA layers, so the higher, the stronger the adaptation. And LoRA dropout, so it just helps avoid overfitting. The higher this number, the more you avoid overfitting, but again, the more you risk underfitting. You give these parameters into your LoRA config, and you also give it the target modules. These are the layers you want to update, to fine-tune. You can, I think in this case I'm doing it for all of the layers, but you can select them as you want. In here I gave it my username and my output directory. This is going to be helpful for it to push my model, my fine-tuned model, into Hugging Face. Now to the training parameters. These are also very important. Now the first two parameters, per device train batch size and per device eval batch size. These are basically the size of the batches that go through in each step, so training and evaluation. Higher numbers allow your model to train faster, but you're limited by your memory size. So if you have more memory, you can use bigger sample sizes here. If you don't, then you can use smaller ones. That helps you not run out of memory. Now, the gradient accumulation steps is the number of steps throughout which we'll accumulate the gradient before updating it. And this allows us to sort of simulate bigger batch sizes. The number of logging steps is the, every 5 steps we're gonna log our loss metrics. Very low numbers will make our model slower when training, but it provides more insights, and when you increase this number you'll have less insights, but then it runs a little bit faster. Learning rate is the initial learning rate for the optimizer, so it starts with a certain learning rate. That's how much your model is able to adapt to new information. Now you want this number, if it's too high, it's always gonna update too much, let's say, to new information, and it might never converge. If it's not high enough, it might take a really long time and still not reach the optimal values. So you need to find something that works well for the amount of data that you have and for how specific it is and things like that. And this learning rate will be updated using a scheduler type. In this case, it's the cosine function. The cosine function here allows us to gradually decrease the learning rate following a cosine curve, helping strike a good balance between speed and learning. The cosine here helps us update the learning rate sort of slowly and smoothly, finding a good balance between speed and stability. This is the maximum length of a sequence that will be used for training. Bigger ones will provide more context, but they also use more memory and more compute power. And the warm-up ratio is just the ratio of the initial step, the total steps that will be used. And the warm-up ratio is the ratio of the total steps that will be used to slowly ramp up the learning rate to avoid sort of like crazy divergency in the training, in the beginning of the training phase, sort of instability. So you use some of the initial rounds to warm up. Now, once you've defined your training arguments, you can create a trainer using them plus the tokenizer we created back then, and then you can train it. Now here I only chose 3 training epochs. This is also very important. The number of training epochs is the number of rounds that you're gonna train your model over. Here I just chose 3 for the tutorial, and you can see here for each epoch the training loss and the validation loss. Ideally, when you have, let's say, 10, you can see how they behave. Usually what you see is like training loss is always going down, and the validation loss, ideally you want it to go down as well. If it's not the case, if it's going up, it means you're overfitting. And then to avoid overfitting, you can play with some of these parameters. For example, the dropout and the rank dimension and alpha. Yeah, these 3 parameters might help you with overfitting. Once you can see that the validation loss converges and it decreased and didn't increase, you can then push your model to the hub using your username and output directory, and then you have your model that you can use as you'd use any other model. So here I've taken the base model and my fine-tuned model, and I've asked both to write an essay on the future of AI to sort of compare outputs just to see if the fine-tuning worked. So we can see the base model output says something like, okay, here's an essay exploring blah blah blah, whereas the fine-tuned model is more in line with how Paul Graham writes. So it starts with these dates, because he always starts with like month, year. So ideally in the dataset creation, we could have deleted that. And then here you can see the rest of the essay. So the future of AI is going to be interesting, blah, blah, blah. And then you can load it using Automodel for causal LM from pre-trained. This is the fine-tuned model, and you can see how it looks, including the two LoRA matrices, plus the parameters of dropout and things like that. That's it. I'm gonna be posting this code on GitHub if you want to use it for your own use cases. Hope you liked it, and yeah, keep on building.